Hi, I'm Toni. Today I'm going to talk about experimental support for RDF and the query language SPARQL and how it all relates to entities. Hi, I'm Toni. Hi. Have you been in my talk last year about entities? Who of you knows about entities? Who has built an entity store? Okay. Do you know any graph databases? Okay, 1, 2, good. So this talk is about a lot of topics. One of them in the center is RDF, a format for graph-like data, and SPARQL, a language for querying graph-like data, and also about entities, how you can query entities using SPARQL, and how you can back entities by graph data. So, but to get to that, in the last slide, we need a lot of preliminaries. So I just start with RDF, the resource description framework. So what is a resource? Every object or every formula or every concept is a resource, and it, yes? Like that? Yeah. Oh, louder? Okay. So every resource needs an identifier, and the resource description framework defines how these identifiers look like, and they are IRIs, which are something like web addresses, but they are a superset of them. Yeah? So here's an identifier for the concept adrenaline, and here's another identifier for a property, the label property. And it's important that we have these long identifiers. Yeah? I'll explain later why. And then there are literals, because you might create an identifier for the number 15, but it's so common that you can just write out the number. And then there are strings, language tag strings, and more complex data type literals. That means, what is a data type literal in RDF? Yeah, so let's see, if you have just a string here, you might not know what it means. But this IRI to a data type defines what this string means, how you have to interpret it. Yeah? So you can, in principle, store arbitrary data in RDF. You can just define your own new data type, standardize it somewhere, publish what it means. And then there are these blank notes. You'll see them later. So from these resources, you can form statements like triples. Yeah? Albert Einstein was born in Ulm. It's a short English sentence, and it has an encoding like that. A subject, predicate, object. This is an identifier for Albert Einstein. Yeah, it's not so human readable, but that's what we have this label property for. Yeah? Here is some property that says born in, and this is an identifier for the German town Ulm. Yeah? And then you collect these graphs together into, you collect the triples together into graphs. Yeah? So this is a triple graph. And various graphs taken together form an RDF data set. And we have a function called graph store. By the way, this is all experimental, and you can't use it yet. So very. So a graph store has a default graph and a few named graphs. Yeah, for instance, this graph contains the population of certain countries. Like this is maybe the latest population. But you have a different data set that refers maybe to a year 1986. And you have a different population for the same entity. So that is one way to model dated data. So let's see how a typical RDF graph looks like. So first, you choose some vocabularies. It's always good to reuse vocabularies that other people have defined, because then when they import your data, it's already unambiguous what your data means. So here are some common vocabularies like RDF and RDF schema. And I also use the time ontology, because that's important in cooking. And then I define some symbols here. Yeah. So if I say RDF of type, I get this long identifier. Yeah? So I introduced some functions to work with them. So, and then I build a graph. Yeah? Like here, my favorite dish, rice with mushrooms. It's of type recipe. Yeah, I didn't want to mint new identifiers, so I used this example namespace. And it has a label, so a machine would know that this is the thing to display to a user when they present you the recipe. Yeah? And then the recipe also has some steps like heating the oil and cooking the rice. And these steps have some temporal relations. Like I'm using the word after from the time ontology. Yeah, that means frying the mushrooms happens after heating the oil. And you need to prepare all of the things before you can mix them. Yeah? And then from the time ontology also I can specify how long certain steps take. And then you can export that in various formats. So there are various formats for storing RDF data, and one of them, very nice one, is Turtle. And it writes out the prefixes that I used, and then in a very compact way groups statements by subject and eventually even by object. Yeah, so it's a very compact representation of that graph. And to see that it's really useful, that you can do something with it, you just import it again. Yeah? Someone else could do that too. And then you verify that these graphs, that the one you started with and the one you just imported are isomorphic. Yeah? And that's what you wanted to do. So homework, build a temporal reasoner that figures out whether all the constraints, the temporal constraints, are satisfied in a given recipe. Yeah. Now, SPARQL. SPARQL is a query for querying this kind of RDF data. And it has various forms, like a SPARQL select query. Yeah? So you start with some kind of simple triple graph that contains like data about fruit, like banana is yellow, and the strawberry has a shape round. And then you write a query that you apply to this fruit graph. And the contents of this query operator are a graph pattern. And this graph pattern consists of one triple pattern. So in this case, every symbol is considered a variable. It's similar to integrate or table, where symbols are the local variables. But we can talk about that, whether that is right to do so. Yeah. And then here's another pattern. We want for every fruit the color, and optionally the shape. So here you see the results. In this one case, you get the color, and the other, you don't get the shape, but you still get a solution. If I remove this optional here, you would just get one solution. Yeah? And there's a construct query that says, from some pattern, use a template to build another graph. So what you get back is another graph. So yeah. And then there's an ask query. So you don't have to return solutions. You can just check, does a certain graph pattern exist in a graph? And in this case, it does. There is a fruit with color yellow. Next. So what we've seen so far, RDF, in-memory, import, export, and SPARQL. But there are a lot of features that SPARQL has, so let's continue with a break. So do you know Wikidata? Yeah, I assumed that everybody knew, but recently I talked to someone and didn't, so I explain quickly. So maybe you've seen the info boxes in Wikipedia, right? Yeah. So this is the German info box and the same info box in Hungarian for the German town Stuttgart. And it gives a different number for the population density. So that means someone should go to the 300 different language versions of that page and fix that. Or now they can go to Wikidata and enter the value there. And then there are some info boxes that now draw data from Wikidata. So Wikidata is made by the same organization that makes Wikipedia. Yeah? What else does Wikidata give you? So before, when you wanted to link to a concept, you might have linked to Wikipedia pages. But then the page name changes because there was a dispute whether there is an accent over the name or not. And then you have to update your data. Even Wikipedia itself had this problem with the language links. Yeah? When one language link was stored in the page, changed, it had to change in 300 other Wikipedia language versions of that page. Yeah? And now you use Wikidata to link your data. So there's one identifier, this Q number here, and it will never change. You can change the label of that item, but it won't affect what you link to. And from there, you link to the Wikipedia pages if you like. But there's also other data, not just links to Wikipedia, but arbitrary data like numbers, quantities, images, and so on. So how do you access that data? Yeah. Before that, you had to parse these info boxes from Wikipedia. And that's what I found, for instance, on the Slovak Wikipedia. Maybe they were missing a hyphen here, but it's not clear what that number means. Yeah. And now you can access the same data without having to read a Wikipedia page. And there's an interface for both humans and machines. The one for humans is here. So you just enter a SPARQL query and get a result down here. But what I talk about now is this machine interface. So there's a SPARQL endpoint that I can query, and the data comes back. And I show you how. So that's what we have SPARQL execute for. It encapsulates a lot of technology that we need. So let's just query. Now I do it live. Wikidata. I just asked Wikidata, the SPARQL endpoint, count all the triples that you have. And I have 3.7 billion triples. It's a lot of data. I couldn't put it in a machine because I don't have hundreds of gigabytes of RAM. So, but we don't want to write some kind of query string. Yeah? Instead, we want to use the symbolic query, and that's possible too. So SPARQL execute takes here a symbolic query or a string, whatever you like. And this one, for instance, finds all items that are an instance of and potentially subclass of a neurotransmitter, and optionally finds a formula and finds the English label. Yeah? And that's it. So I can quickly change that to German, and yeah, I see the German label for all of them, or any language that you like, together with the formula. Another example, taxonomy. You start from a whale and retrieve all the parent taxons and retrieve, you build a graph from it. Yeah, it starts here at the whale and it goes to life or whatever. Yeah, or some really fancy query. Yeah, you say Albert Einstein had an employer who was of type university, and there was a start date and end date associated with it. And there also Halley's Comet passed by a couple of times Earth, yeah, also has a date associated with it. And then you filter that. And then you figure out, well, that graph pattern has one match. Yeah, and that's when 1910 Halley passed. And in between 1909 and 1911, Albert Einstein was at the University of Zurich. So, I still have time. Oh, no. OK, you can use SPARQL not only to query SPARQL endpoints, but it's a nice language. So I'm just going to quickly show how you can do queries against built-in entities, for instance. Yeah? So here you can do basic things that you can do with our current entity framework too. Yeah, like retrieving for each country the population and the area. And the results is some association. Yeah? For each subgraph that match the pattern, you get the bindings for the variables, like the United States has this population in this area. Yeah? And I just limited to 3. Yeah? So, yeah. Or reverse lookups. Find all movies starring Bud Spencer. Or mountains in Italy higher than a certain height. Or, again, movies by Bud Spencer, but this time also retrieve the image. Yeah? A little bit more complicated, an arbitrary property chain. That is actually tricky to do currently. Yeah? So you start with Germany, go to the bordering countries, and then for the bordering countries, take the capital city, and from that the population, and return all of that data. Yeah? It's also spanning 2 domains, country and city. Yeah? Or aggregation. Find the largest European countries by number of bordering countries. Yeah? So aggregation we don't currently have in Entity Framework. So you would have to write your own complicated code. But SPARQL provides aggregation, and it's doing the entity queries for you. Here, another example, but I'll continue a little bit more. Here's something crazy. So a simple sounding query like finding by geographic region the longest river is actually, quite complicated. So if you come up with a more simple query, well, let me know. This one uses a subquery, and I found it somewhere on the internet and translated it to the symbolic SPARQL query. Yeah. So we saw a few more things. So I hope this graph gets green soon. So from SPARQL inspired, we have a few new functions. Also, everything experimental, nothing in any product yet. So graph cases. Let's start with some graph that has some cycles, and let's find all cases of a graph that matches that pattern. Yeah? It starts from x goes to y, from y to c, and from c back to x. And we don't want any duplicate cycles there, so we constrain x, smaller y, smaller z. Yeah. Oh, and then we want to see the labels again. And we see these two matches from that. Yeah? So we have some kind of subgraph matching. Or we can just use a rule, like in cases, to extract the data, because I might not be interested in the graph, but in the actual data. Or property paths. Yeah? You start at 1, end at 200, find all the paths, and then return the nodes that were visited, no, the edges that were visited. Yeah? So there's one that goes along here, and another path that goes from 1 over 77 to 200 directly. Graph matches. Sometimes you're just interested in the bindings of the variables. Yeah? We don't have a corresponding Wolfram language function in general pattern matching yet, but this is an idea. And other functions like graph member queue, it's similar to the SPARQL ask query. Yeah? Does a certain pattern have a match? SPARQL update. So there's a whole language for updating graphs in SPARQL. And here's an example. So you start again with a fruit graph, and you insert some more fruit. Yeah? Or, yeah, this is for explicit data. Or you have a more complicated graph of geometric objects, and you match some kind of pattern, and from the solutions of that pattern, you populate a template. That means all objects that have a radius, you want to insert also the diameter, which is 2 times the radius. Yeah? So now you have a new graph that contains the diameter, yeah, which it didn't before. And there are various other functions. So let's do an interesting thing. So this is some kind of medical research. So if you heard about drug repurposing, which medical drug can cure a disease, repurposing means that you might be able to reuse it for another disease. Yeah? But you need suggestions of how to do it. And this paper tried to do data analysis on a lot of public data sets to find suggestions for where to do research. And I converted this data to RDF. And I can start my local server here. I'm not going to do that now. And have a local SPARQL endpoint running on my machine. I did that yesterday, and it has 2.3 million triples. Yeah? And oh, here they find some prefixes. I'll lead later. And then look up treatments. Yeah? That means find all compounds that treat a certain disease and return the labels, because we are humans. We want to see what it actually is. So when we see that compound treats that disease. Or find the number of all treatments in that database, 750. And then find all the combinations of compound disease. Yeah, it's like 200,000. That means there's a lot of potential for combinations of treatment to disease that might be investigated for repurposing. So let's look at paths. So I want to find a path between this arbitrarily chosen substance and this disease to see whether it has a path that follows the properties upregulates and interacts with and associates. Yeah? So this thing upregulates the gene, and this gene interacts with the other gene, and it's associated with a certain disease. Yeah? And we see a few solutions, but there are thousands paths of that particular type. So now let's count for all substance disease pair how many paths are there of that type. And you see, for instance, for this case, there are more than 3,000 paths of that particular type. So now, as your homework, write a program that generates all path types, and then count all the paths for all types, and then build a classifier that predicts whether a certain compound disease pair might be a treatment. Chemical structure. don't have enough time to explain that example. It's about looking. No, I won't explain it. You can also query custom entities using SPARQL. So let's create some fancy entity store. It contains statements. That means, for instance, the water boiling point has 3 statements. These statements contain values and references. And these references have associated authors. And if you want to query such a complicated structure using entities, you're stuck pretty soon. Yeah? So for instance, the walking speed of a dog, you get back 2 statements. And from the statements, you have to look up the value and reference. Yeah? With SPARQL, you can do much more complicated things. For instance, look up all the values that have been reported for the walking speed of a dog. Yeah? Or all the values that are also referenced using, for instance, SPARQL exist. Yeah? And then you can maybe read that on your own, but it's about finding in the data authors that have reported suspicious values, and in queries at the end excluding all of the values that have been reported by suspicious authors. Yeah? So we have covered nearly everything, and now let's come to the most complicated topic, trying to build an entity store from an existing graph database. So Wikidata has more than 3 billion triples, and it's a lot of data. So I would like to build an entity store that contains a view and a part of that data. And it's actually tricky to do that because it's graph-like data, and entities are some kind of rectangular view. So here's some experimental way to specify what kind of data and what kind of entities you want out of that huge graph. And what you do is, for each type that you want to define, in this case, I'm interested in lakes and rivers in Spain, you define an entity filter, which can be an arbitrarily complicated SPARQL query, but in this case, it's just something that says, hey, it's of type lake, and it's in Spain. Yeah? These are all the entities for that type. And then you define properties. The value of a property might not be simple. It might be distributed over the graph, like the unit and the magnitude are different values in the graph. So you need a way to locate these values, associate them with the correct entities, and later post-process these things to turn it into Wolfram language quantity object. Yeah? And let's just see it, how it works. So it looks like entities. You can't distinguish them anymore. So entity list works. You see a list of entities. So there's 442 lakes just in Spain, known in Wikidata. You can look up the length or an image. Yeah? So the image is retrieved. So you retrieve from the database a link to the image, and then it's imported. Yeah? So you can do entity class lookups. Like here, give me all the rivers that are longer than 900 kilometers. Yeah? This is translated into a SPARQL query, and it's done efficiently on the Wikidata servers. So it means no waiting on your side. Yeah? Or even more complicated, let's try to find all the rivers in some geographic region. Yeah? Also an entity class query, and returns a result. Find all the lakes around a certain point. Or retrieve a data set for a single lake or a whole collection of rivers. And I think my time is up, and we went through. Thanks.